afternoon, everyone, and welcome to today's presentation by Dr. Andy Ryman, the Westchester Forest Inventory. What does it mean for Rockland? My name is Suzanne Barclay. I'm the Executive Director of Cornell Cooperative Extension of Rockland. I believe we have some land use board members and perhaps some municipal park staff joining us along with members of the public, so thank you all for being here. Today's presentation is the fifth in our Sustainable Suburbia series that is funded by a grant from the School of Integrative Plant Science at CALS, which is Cornell's College of Agriculture and Life Science. This series addresses three major environmental issues in Rockland: rampant invasive plant growth, our limited water supply, and an overabundance of deer. Our drinking water supply, you may know, is essentially limited to the rainfall that falls within our borders and is captured in our reservoirs or absorbed in aquifers and wells. Last year, right before the pandemic closed everything, the Rockland Water Task Force released their newly created water conservation plan. And in the plan, there's a role for each of us. So that's businesses, government, and community members to understand our water supply and to learn how to conserve it. And in fact, we will be presenting another series this year on the sustainable landscape. So watch for those notices, please. In Rockland, invasive plants and insect species and our burgeoning deer population have together made a devastating impact on our forest and woodland areas. The invasive insects include the emerald ash borer and now spotted lanternfly, although I don't believe we've seen damage from it yet. However, we have seen the damage from deer. Deer eat anywhere from 8 to 12 pounds of vegetation a day, and they are literally consuming the understory in our woodlands and significantly altering that ecosystem. So today's speaker, Dr. Ryman, is an ecologist and a geochemist who specializes in plant ecophysiology and the terrestrial carbon cycle. He has a joint appointment at the Institute for Sustainable Cities and the Advanced Science Research Center at Hunter College. After Dr. Ryman's presentation, we'll open the floor for questions. And we'll do that by using the chat box at the bottom of your screen. If you're not familiar with chat, just look for that white bubble, click on it, type in your question and press enter, and I'll make sure Dr. Ryman hears it. And at the very end, we'll ask you to complete an online survey as a way for you to give us some feedback. And we'll give you time to complete it, but if for some reason you have to leave early, just let me know and I will email it to you. So I want to thank our communications manager, Charlie Payne, who makes these presentations happen, and our horticultural educator, Kristen Osman, who has partnered with me on this series. So again, thank you for attending today, and now let me turn the screen over to Dr. Ryman.
All right, great. Can you see my slide okay?
Yes.
All right, great. Well, thank you for that great introduction. So as mentioned, my background's in forest ecology and urban ecology. A lot of my focus is on things kind of related to the carbon cycle. I'll mention in a minute why I think that that's important. And so today I'm going to talk a bit about some of the research that we've been doing that kind of sheds some new light on how to think about the forests and the trees sort of in and around the communities where we live in a way that is quite a bit different than the places we traditionally think about forests. So thinking about places like Harriman State Park or the Catskills or the Adirondacks, those vast expanses of the forest, as I'll show you, sort of function a little bit differently than the ones in and around our communities. And then I'll talk a little bit about this sort of natural resource and forest inventory project that we're working on in Westchester, and how sort of the approaches that we're developing there and the products that we're developing might be useful for folks in Rockland County and beyond. So first, I have this great fascination with trees. And when I did my master's work at University of Maine, there were all these other graduate students that were studying like really charismatic things like moose and lynx and bears and bobcats. And they had these great pictures of charismatic megafauna. And I was always a little bit envious of the pictures that they get to show. And then a few years ago, I heard a talk from a great dendrochronologist at Harvard Forest, and he referred to trees as charismatic megaflora. And I really, really gravitated towards that. And in my mind, I think there's no tree that sort of deserves that title, maybe more than our sugar maple trees. So of course, like there are these beautiful organisms in the fall, and they are responsible for giving us maple syrup, which I think is one of the most delicious things that exist. And so I like to go with this term charismatic megaflora when talking about our trees. And there's a lot of reasons why we should care about our trees and be concerned about them and trying to increase, sort of the coverage of trees around us. And a lot of that comes back to the wide range of important ecosystem services that they provide. So we're all probably quite familiar with their role in providing habitat and biodiversity. They're really important for recreation and aesthetics. Certainly during the pandemic, this has become even more clear. I live in Westchester now. I'm from Rockland County. I spent a lot of time in Harriman State Park, and I know how much busier those places have gotten over the past year. They're also really important in dampening noise pollution. If you sort of live near a busy road and you're fortunate enough to have some forest in between you and the road, you'll notice that especially during the growing season when we have leaves, that sound is a bit quieter than it is during the winter. They're also really important in maintaining water and air quality. They're important for regulating water flow in our streams and other waterways. And they're also a really, really critical component to climate regulation, both at global scales, which we hear a lot about, and also at local scales. And so this is sort of what I'm going to focus on today. At global scales, trees and forests are important in climate regulation because they sequester carbon. And in doing so, they can greatly slow the rate of carbon dioxide accumulation in the atmosphere and slow the rates of climate change. At local to regional scales, they're also really important because of roles that they play in thermal regulation. So they do this through shading, which we're all quite familiar with, but also through other processes like evaporative cooling. So trees are really, really efficient at moving water from the soil to the atmosphere. And that evaporation and transpiration process consumes a lot of heat and cools the air around it. I sort of liken trees to kind of like the Earth's sweat glands. And you may notice on a hot day when you're sweating and as a breeze comes across your sweaty arm, you can sort of feel it cool off. What you're feeling is the heat that's getting consumed to evaporate that water that's on your skin. And at a larger scale, our trees are kind of doing the same thing and cooling off our land surface. They also change the color of the Earth's surface, especially as we'll talk about in a bit, in comparison to lots of developed land covers. Trees are lighter in color, which means that they're reflecting more of incoming solar radiation and play an important role in cooling things off that way. And so these are the components that I want to focus on today. And I'm going to start with sort of the carbon piece to all of this. So to kind of put things in perspective, at a global scale, forests and other terrestrial ecosystems, so these are our ecosystems that are on land, offset more than 1/3 of all of the carbon dioxide emissions that humans put into the atmosphere through fossil fuel combustion and land cover change each year. And so in doing so, they're having a huge impact in slowing rates of climate change. What drives this process is sort of the delicate balance between the carbon dioxide that plants take out of the atmosphere through photosynthesis and the amount of carbon dioxide that gets released back to the atmosphere from these ecosystems during the process of respiration. And what drives how much carbon gets sequestered in a forest is really the small difference between these two terms. And both of these processes are highly sensitive to climate conditions and other environmental conditions. And as a result of that, a big focus of a lot of my research is to try and understand how different aspects of human-induced environmental change might alter tree growth and overall forest carbon sequestration. And then more recently, since I started at CUNY a couple of years ago, we've been starting to do more and more work sort of investigating how trees can be used to mitigate climate change at kind of local scales and also contribute to mitigating climate change at larger regional or global scales. So when we think about forests and forests sequestering carbon, these are the sorts of places that many of us think about. And in fact, these are the sorts of places that most ecologists have gone to for decades, if not centuries, to better understand how forest ecosystems function. So on the top left there is a picture from Harriman State Park. On the right is a picture from the Adirondacks. And these are these vast expanses of what we would characterize as intact forests. But as I'll show you in a minute, a lot of our landscape is looking more like perhaps this image on the bottom, where we have this heterogeneous mixture of development and agriculture and little patches of forest. And when we think about how land cover change impacts carbon storage, we mostly focus on the areas where forests were lost. So in this case, forests were lost to create that agricultural field. And we don't focus as much on what happens to the forests that remain. And I'm going to go into this in a little bit. But generally, we've made this assumption that this little patch of forest in this agricultural landscape sort of sequesters carbon and responds to environmental conditions the same way as this sort of large intact forest might. And what I'm going to show you is that this is actually not the case. And as a result, it's important to think about our forests, not just as forests, but more broadly in the landscape context that we find them in. In addition, these sort of suburban and urban landscapes, carbon cycle scientists for a long time just had no idea what to do with them, right? There's clearly some vegetation there, but it's not quite forest. And so we just sort of put this big question mark on it. We don't know what they're doing from a carbon perspective. When we think about carbon sequestration at a regional scale, we might use satellites and other sorts of data to quantify, in this case, net primary production, which is just tree growth. And you can see these white areas all scattered around Massachusetts. Those are areas that are just totally omitted from these calculations because they look like this picture in the bottom right, and we don't really know what to do with them. In the case of Massachusetts, that represents about a third of the total land area that just totally gets ignored. And I'm also going to show you that that is a really incorrect assumption, and these landscapes can actually be really important. So a lot of the work that I'm going to talk about sort of really focuses on these two components. So at a global scale, about a quarter of the world's temperate forests, so that's the area sort of across much of the US and much of Europe here and then into parts of Asia, about 25% of all that forest area are less than 30 meters of an edge. You can see here the areas of highly fragmented forest are in the red, the really intact forests are in the blue. And when we look closer at New York, while New York has a lot of forest cover, I'll show you some data on that in a little bit, nearly 20% of all of New York's forests are within 30 meters of an edge. And this 30-meter number is important. I'll come back to that in a little bit, because this is the area of forest that seems to be impacted by the presence of that sort of non-forest land cover adjacent to the forest. When we zoom in a little bit, so I apologize that Rockland is mostly cut off here. I put together this figure for a presentation I gave in Westchester a few weeks ago. But you can see, the forests are highly fragmented. The green areas of forest, the areas in purple are forest areas that are adjacent to some sort of development. The areas in yellow are forests that are adjacent to some sort of agriculture or vegetated land cover. You can see little snippets of Rockland County here. Again, highly fragmented forests. A lot of the forest is adjacent to developed land covers. Why is this important? Why am I spending all of this time showing you pictures of fragmented forests? Well, when we create a forest edge, we can radically alter the growing conditions and the microenvironment that the forests that remain on our landscape experience. So for example, we know from a lot of research in fragmented forest ecosystems all over the world that forest edges are hotter, drier, and windier than intact forests. But they also have greater access to light and nutrients, right? So there's these maybe series of pros and cons of being a tree near a forest edge. When we think about this in the context of like Rockland County or Westchester, These are also urban/suburban landscapes that themselves have a distinct suite of growing conditions that are far different than what an intact forest might experience. So for example, these landscapes are hotter and drier than rural landscapes. They experience higher amounts of pollution, but they can also experience higher amounts of nutrient availability. And so collectively, we can think of these processes of forest fragmentation and urbanization as creating sort of these series of risks and opportunities for forest growth and the ecosystem services that are more broadly provided by trees. And so for the next couple of slides, I'm going to show you some data from some research we've been conducting in Massachusetts over the last 5 years or so, where we're comparing fragmented forests to intact forests in sort of urban landscapes in the greater Boston area, much like a lot of the landscapes that we see in Rockland County and Westchester, and in rural landscapes in central Massachusetts. So maybe more similar to what you'd find if you went up to like Dutchess County or parts of Ulster or Orange County. And for this work, we set up all of these field plots. We run these transects that go from the forest edge to the forest interior. We collect a lot of tree cores to quantify rates of tree and forest growth. We make all sorts of other measurements of tree and forest biomass, and we measure respiration in the forest. We do this whole suite of measurements. And in the end, what we find is a couple of things. First, in this graph that I'm showing you, forest growth here is on the y-axis. And we talk about forest growth in terms of the area of wood that the forest produces each year. And as we go from the forest interior, which is these blue points here, to the edge, you'll notice a couple of things. First, we get this huge increase in growth. In fact, we find that generally forests growing near an edge grow about twice as fast as the forests in the interior. And you can sort of see that in my little cartoon here. These forests on the edge are removing way more carbon dioxide from the atmosphere than the forests in the interior. But the other thing I have going on here is on the x-axis is the number of days in the early part of the growing season that are sort of above the average high temperature for July. And what we find is that essentially in our cooler years, this magnitude of this forest edge growth enhancement is considerably larger than it is in our hotter years. And while forests, whether you're in the interior or the edge, as they're exposed to more and more heat or hotter and hotter growing conditions and growing seasons, the rate of growth declines. That rate of growth decline is 3 times faster in our forests near the edge and in the interior. And so this is sort of suggesting that fragmentation on one hand is boosting carbon sequestration per unit area of forest, but it's also maybe increasing how vulnerable that carbon sink is to a changing climate. These are data from our urban suburban plots in greater Boston. If we contrast that to what we see in a rural forest, we see a bit more of a muted response. So here, again, these blue points, that's the forest interior. Those forests don't really seem to exhibit that same sensitivity to heat that our urban forests do. And when we get near the forest edge, while there's still this decline in growth, so the fragmentation is increasing the sensitivity of these forests to heat, that decline in growth is considerably smaller than it is in our urban forests. And so from this, what we find is that there seem to be these synergies between forest fragmentation and urbanization that are kind of exacerbating how sensitive a forest and carbon sequestration are to heat. And this is indicating that kind of the way we think about forests and how they sequester carbon now and how they might continue to sequester carbon into the future really depends on where that forest is and what's around it. And so I'm coming back to my example here of Massachusetts. So across the state, we find that about 28% of all of the forests in Massachusetts is being influenced by these edge conditions. But depending on where you are, those dynamics are quite different. So Petersham, Massachusetts, this is a rural part of central Massachusetts where Harvard Forest, where we conducted our rural research has very little forest fragmentation. If we contrast that to the other end of the extreme in Boston, where essentially all of the forest is being influenced by edges, what we can conclude from this is that our forests in cities, and I would argue in our suburban areas too, are more productive per unit area than our intact rural forests. But because of that data that I just showed you, these urban forests are also likely going to be more negatively impacted by climate change. And so on one hand, the forests that are around us in Rockland County and Westchester and New York City, for every unit of area that you have that's forested is going to be more productive than a rural forest. But our climate is no longer this like sort of stagnant thing. It's quite dynamic. We know it's getting warmer. And so this brings up a lot of uncertainties about sort of how we think about some of the ecosystem services that our forests might provide moving forward in time. Another thing that I want to talk about is not just sort of the forest that we would sort of identify as forests, but other aspects of trees and canopy cover. And so to do that, let's talk a little bit about kind of the composition of New York State, right? So the state on the whole is nearly 2/3 forested. The second most common land cover is agriculture or old fields. About 10% of it is developed. And so this map here on the right, you're seeing those different land covers. The reds and the pinks are developed. The different shades of green is forest. The yellow is agriculture. The brown here is also different sorts of agriculture as well. But when we look at just tree canopy cover, so this can be trees in a forest or it could be trees in your backyard, we see that the state actually looks quite a bit more vegetated than it does if we just look at land cover alone, right? So I'll toggle through these again. You can see in the bottom of New York where Rockland County is, you get a very different picture when we just look at the tree canopy cover versus land cover. And when we take all this into consideration, oh, sorry, I have my little zoomed in area here that includes Rockland County. So here's the land covers. The darker the red means more densely developed land. The lighter the red is maybe sort of more like sprawling suburban land. And when we look at what canopy cover looks like, you can see that it's not just our forests that have a lot of trees, right? It's these developed areas as well. And at the scale of New York State, these trees that we plant in our residential areas, maybe scattered in our agricultural landscapes, add an additional 0.3 million hectares of canopy cover to the state. So I apologize for using metric if you're not familiar with metric, but basically 1 hectare is about 2.5 acres. So another way to think about this is like adding almost an additional 1 million acres of tree canopy cover by taking into account the trees that we plant along our streets and in our yards. And so because of this, I would argue, and I hope to convince you, that our residential areas can really provide an important opportunity for carbon sequestration. So if we think about this little development here, there's forest around it, there's a whole lot of houses in the center. It's not that uncommon of a type of suburban development. Typically, we would sort of mask out that whole area and assume that it's not doing anything from a carbon perspective, right? This takes us back to that model that I showed you that is predicting carbon sequestration across Massachusetts. It would do the same thing across New York. It just ignores these areas. But our work across Massachusetts, and we would see the same things in New York, suggests a couple of things. First, in this graph that I'm showing you, carbon flux here is carbon being released to the atmosphere. Anything above zero, this is emissions associated with land cover change. So when we clear forests to put houses there, typically the trees that are there are either getting chipped and decomposed quickly, or they're getting burned, in which case that carbon gets returned to the atmosphere pretty quickly. That's what these emissions are. And then we have our forests that remain on the landscape that are still sequestering carbon. And you can see in rural areas that are experiencing very little development, there's almost no emissions from land cover change. There's a large forest carbon sink. But in the more suburban counties, in this case, just outside of Boston, the ratio of emissions from land cover change to carbon sequestration are quite a bit larger, indicating that at some point, maybe if development continues, these sorts of counties will be a net source of carbon to the atmosphere just from land cover change and the sort of terrestrial ecosystems. But we know that these residential areas include a lot of trees and may also provide important opportunities for sequestering carbon. The reason that I say that is some of our work from a handful of years ago, we compared rates of tree growth from trees in a forest versus trees in a residential area. And not only that, we looked at how growth rates of an individual tree changed as it went from being in a forest to being in a residential area. And what we find is that these trees in our residential areas, in our communities, grow about twice as fast as those in forests. There's been some other work just looking at street trees, and you can see the same pattern with the exception of really large trees. Those street trees are growing considerably faster than the same size tree in a forest. For the street tree component, it's important to also include this caveat that these street trees tend to die younger. They're kind of like the rock stars of the tree world. They kind of live fast and die young, but it also imparts opportunities there for tree maintenance to kind of help them to live longer and maybe continue to take advantage of their sort of high carbon sequestration rates. So now if we come back to this graph that I showed you earlier, this graph that I showed you is sort of the way we would normally think about carbon sequestration in these landscapes, where we just ignore all of these trees in these developed landscapes. But because we know that these trees grow considerably faster, we can sort of plug that into our estimates. And if we assume that at least on the high end, these trees in our residential areas are growing twice as fast as the forest trees, it greatly changes our estimate of how much carbon our landscapes are sequestering. And it really highlights that by boosting canopy cover in our communities, in our backyards and along our streets, we can really go a long way towards offsetting some of the declines in carbon sequestration that occurred when we removed the forest and put the houses there to begin with. So I want you to kind of keep that in mind as you're moving forward, that it's not just forests that are important, but it's also the vegetation that we keep in our communities. So the other aspect that I mentioned that is really important about trees and climate is their role in sort of thermal regulation and cooling the area around them. And to really think about what that means and why that's the case, we need to just briefly explore the idea of what the urban heat island is. So I'm sure many of you are familiar with this term, but basically it's referring to the commonly observed phenomenon that as you go from rural vegetated landscapes to more and more developed landscapes, air temperatures can increase considerably, right? So in New York City, the estimates are that New York is maybe 3 to 5 degrees Celsius warmer, so maybe 8 degrees Fahrenheit warmer than it would be if it wasn't such a built up city. That's on one extreme, but even places like Boston are about 5 degrees Fahrenheit warmer than they would be if it wasn't a city. This is important for a variety of reasons. It doesn't just simply make things hotter, but it can exacerbate the intensity of heat waves and the related public health impacts. So an example of that comes from the big Paris heat wave in 2003. Where you can see that there were these massive spikes in mortality as those peak air temperatures ramped up. This, of course, was exacerbated by the fact that Paris is a city and is much hotter than the surrounding countryside. Also, from an energy consumption perspective, the urban heat island is responsible for up to nearly 10% of all of the electricity demands in the US. So just the extra cooling that we need to offset the hotter conditions in our cities is responsible for almost 10% of our electricity demand. So this introduces a huge source of inefficiency in our energy demand system. And because most of our electricity is coming from some sort of fossil fuel source, this is greatly increasing carbon emissions to the atmosphere. The other thing that these hotter conditions in cities can do is exacerbate pollution issues. And a really good example of this is photochemical smog, also known as ozone. And because this process happens during high sunlight conditions and is accelerated during high heat conditions, we tend to get sort of those ozone alert days on our hottest days of the year. And that just gets magnified as sort of the urban heat island effect increases. There's also these important interactions between the urban heat island effect and climate change. So here's a map that, that was published a few years back that's just sort of showing the estimated or projected changes in the number of days that we can expect to find maximum temperatures above 90 degrees Fahrenheit. You can see in our region down here in southern New York, it's about a 4-fold increase from what it was historically. So we'll get in the neighborhood of like 40 or so or more days each year that are above 90 degrees Fahrenheit. On top of this, there's been, oh yeah, right. So just to give you an idea of what that feels like, that makes our summers kind of more like what they are now in South Carolina. I'm a winter person, I like the cold weather, and so the thought of that just kind of terrifies me. But there's also these interactions, like I mentioned, with urban heat island. And it seems that these projected changes in climate will also exacerbate the impacts of urban heat island in our part of the country by about 20 or 30%. So it's not just a linear shift in temperatures, but there are these synergies here that will likely magnify what that urban heat island effect looks like. So now to think about why trees are important in mitigating this, I like to walk through this pretty simple cartoon of why we have an urban heat island. So this is my cartoon showing sort of our forested landscape and then sort of our urban landscape, which is sort of what the forest would have gotten converted to. And at the heart of the urban heat island effect is really the fate of incoming energy. And the source of that energy is overwhelmingly from the sun. In our cities, because of combustion, there's a small addition of sort of what we call anthropogenic heat, but the overwhelming driver of the urban heat island effect is what happens with that energy coming in from the sun. So the first thing is there's some proportion of all that incoming solar energy that just gets reflected back into space. That's called the albedo. And this is what I was talking about earlier with the trees being a lighter color than many of our like rooftops and streets and things like that. Because of that, our forests are reflecting about 14% of incoming light, while our cities are only reflecting about 3%. On top of that, because we have so little vegetation in our cities, the evapotranspiration, that's sort of like I mentioned earlier, the trees kind of acting like the sweat glands of the land surface, that is less than half in a city of what it is in a forested area. And then this sensible heat flux, so this is like that heat that you can feel, right? The temperature, that is also quite a bit higher in a city than it is in a forest. And what you're left with is there's only 2% of incoming energy that's stored as heat in a forest, but there's 5 times that amount in a city. And all of this is what ultimately drives our cities, and I use the term city here loosely. It could be our neighborhood. You can see this operate at scales as fine as like your driveway. When you walk out onto your driveway on a hot day, if you're not wearing shoes, you notice this in a hurry. So you don't need to be in a big built up place like Manhattan to experience these sorts of things. They can operate at small spatial scales. But at the end of the day, these changes in how energy is getting partitioned between a forest and an urban area is driving how much heat these systems store and how much hotter they are than they would be if they were never urbanized to begin with. And I want to just make sure I emphasize how important this evapotranspiration piece is. Again, it's analogous to that cooling feeling you get when sweat evaporates from your arm. It's a critical role in cooling us off, especially during hot conditions during the summer. We can see this in real time using thermal imagery. So here, this is a thermal image of a research site we have in Maryland. On the left is what this area looks like in an actual image. On the right is sort of the temperature of all of these surfaces. A couple of things that I want to draw your attention to first. The yellows and greens here are indicating the much cooler temperatures than what you'd find even in this grassland in the foreground. You can see the mowed area of that grassland is considerably hotter than the part of the grassland that's not mowed, which is hotter than the forest. The other thing is you can see the heat from this dead tree, right? So we can see this dead tree over here. That tree doesn't have leaves, it's not transpiring, and it's considerably hotter than the living trees around it. At a landscape scale, these things can really pop when you look at a place like New York City. So on the left here, I'm showing you canopy cover, and you can really see where all of the parks are. So here's Staten Island, here's Central Park, here's Forest Park and Prospect Park and Van Cortlandt Park. Those are areas have a lot of canopy cover because they have a lot of forest. And those also correspond to the parts of the city that are the coolest, right? There's a huge range in that surface temperature. Just to point out, surface temperature is not the same as air temperature. This is the temperature you would feel if you touch the surface of the earth. Spatially, it's correlated with air temperature, but numerically, it's not exactly the same thing. But this really highlights the importance, again, of canopy cover in cooling things off, even in a really dense urban landscape like New York City. There's a nice / unfortunate example of this from Worcester. So it seems like many of you are familiar with the adverse impacts of invasive species. And in, I think it was 2008, Worcester had an outbreak of the Asian longhorn beetle. And to deal with that, what they had to do was quarantine areas of the city and just cut down all of the trees to get rid of the insect's food source. And so what that did, this is one of the communities where that happened. This is what that community looked like afterwards. So just go back to the before, you can see all the trees there. Afterwards, there were almost no trees there. And this group from UMass Amherst, it was someone's master's thesis, decided this was a great opportunity to really quantify what the cooling and energy benefits of trees might be in our communities. And so they got utility records and they quantified consumption in these neighborhoods. And so before the insect outbreak, this community had nearly 40% canopy cover and used a little over 7 kilowatts per cooling degree day. After they had to cut down all the trees, that 40% canopy cover was reduced to about 7% canopy cover. And you can see that that cooling costs increased considerably. In fact, that represents about a 40% increase in energy consumption just for cooling. Given the density of these houses, that results in an increased carbon emissions to the atmosphere because of the electricity generation of 0.7 megagrams of carbon per hectare of land. I realize that seems like a little bit abstract, but to give you an idea of what that means, just to compensate for this increased carbon emissions associated with electricity generation, you would need to add 1/3 of a hectare, so nearly an entire acre of forest land for every hectare of housing developed land that lost canopy cover, just to offset that increase in electricity consumption. So this is a considerable impact of losing canopy cover. There was also some work done across New York City to try and understand the impacts of different options of green infrastructure to mitigate the urban heat island. And what they found, there's a lot going on here, but the things I want you to focus on are sort of these reductions in temperature. This is sort of borough by borough and even within borough. And there were curbside planting. So this was just sort of planting trees on municipally owned land along sidewalks and streets where that sort of land was available. This is the estimate of the decline in temperature at the scale of the neighborhood or the entire city. And then the other approach that they looked at was light surfaces, so white roofs. There's a lot more roof area in New York than there is area to plant trees. And so because of that, painting roofs white has a larger cooling impact than trees. But if you look at a per unit area basis, the trees are actually far more effective at cooling. And this is because they're changing the amount of incoming solar radiation that gets absorbed, but they're also transpiring and cooling things off that way. So all of this is to say that these carbon benefits and cooling benefits of trees were a real big motivating factor in this Westchester County forest inventory that we're doing. And I should mention that while this research is focused on Westchester, it's not meant to be Westchester specific. This is work being funded by the DEC's Hudson River Estuary Program. It's a collaborative project between CUNY, Westchester County government, nonprofit organizations, and the DEC. And we focused on Westchester largely because it exhibits a large range in land covers. It goes from really dense urban areas like Yonkers to sort of these more rural, ex-urban feeling areas in the northeastern part of the county. And so it provided a good way to kind of test our approach. And so the objectives of this were to map current and recent changes in land use and land cover, assess the success of community tree planting programs, highlight forest conservation and afforestation priority areas, and also provide guidance for other municipalities or counties to be able to replicate this analysis. And I think the coolest part about this project is that the idea is to do this using entirely freely available data sets. And I think this piece is important because then you don't need the same resources, let's say, that Westchester has to do this. By using freely available data sets, we think that most people, as long as they have some experience using GIS, can reproduce much of what I'm going to show you now. So we do this using a lot of data from satellites. We focus a lot on the Landsat satellite, which sort of floats around about 2,000 kilometers above Earth. A partnership between NASA and the USGS has developed this 30-meter spatial resolution. So what that means is for every 30 by 30 meter pixel of land, they've developed a land cover product that assigns a particular land cover to each one of those pixels. You can get that by going to this website. This is what that looks like. You can download sort of raster layers and calculate everything that you want and manipulate it in however way you want. But they also have sort of bare bones web interface that allows you to kind of explore land cover types. And this is sort of what that would look like. You can zoom in on different areas like Rockland County. On the left here would be the legend showing you what the different land cover types are. They have these every few years dating back to 2001. So it's a really nice way to see how things have changed over time. And so using these sorts of data sets, I'm just going to walk you through some of the things that we've been finding for Westchester, and then I'll finish up just sort of highlighting some of the ways we can think about using this in places like Rockland County. So here's one of these maps that we can very easily generate for Westchester and the different land cover types here on the left. As we might expect, the southern, more densely populated parts of the county are much more developed, while the northern sort of half or third of the county has a lot more vegetation and forest cover. At the scale of the county, nearly half of it is developed. And there's been an increase of about 26 square kilometers of developed land areas since 2001. There's about an equal amount of land that is forested, and the forest cover has declined by nearly 27 square kilometers since 2001. So you can very clearly see that this forest was being replaced by development. That's the largest driver of forest loss in this area. We can also quantify spatial variations in impervious surfaces. So these are things like rooftops and roads. About 13% of the entire county is an impervious surface. And we can also look at not just forest cover, but overall canopy cover. Again, this brings in the idea that the trees that we plant, the trees that we have in our yards are a really important component of the overall tree canopy cover of an area. And when we do this, we find that nearly 53% of the county is covered by trees. This, like forest area, has been declining over time. We've lost about 20 square kilometers since 2011. And I'm sorry, since 2001, I think that should read. But what we find is that more than 10% of the entire canopy cover of Westchester is from these trees in our residential areas, right? So there's a lot that's in forest, but there's also a pretty important component that's in our developed landscapes. We can zoom into these areas and really look in pretty fine detail what these land cover types look like. So here I'm showing you an area around Pleasantville. This is where I live. You can see some of the parks here in green, but you can see in these developed areas that those lighter shades of green indicate that there's canopy cover. You can also see the areas of impervious surfaces, and of course, impervious surface cover and canopy cover tend to be inversely correlated with one another, but they're not mutually exclusive, right? Because you can have trees that are put in a sidewalk and hang over that impervious surface area. And in particular, if you focus on some of these more developed areas, you'll see that while they have a high amount of impervious surface area, they also have canopy cover as well. The other thing that we've been doing is making use of some really cool other sensors that are floating around in space. There's one on the left here is called EcoStress. It's on the International Space Station. On the right is our good friend Landsat. And they have these instruments called thermal radiometers on them. It's really sort of the same technology that now we're all familiar with, where you shoot like a little gun to someone's forehead to get their temperature. These are essentially doing the same thing, but for the Earth's surface. And we can start to look at how temperature varies across the landscape and over time, and the role that trees may be having in sort of modulating what that looks like. So on the left here is a map showing spatial variations in land surface temperature. I apologize that some of these go back and forth between Fahrenheit and Celsius. I sort of have pulled them from different presentations where the audiences were a little bit different, so sorry about that. But you can see across the county, at sort of a spatial scale of 30 to 70 meters squares, the temperature varies from, on this particular day where we collected these measurements, from 62 degrees to 76 degrees, right? This is a pretty small area to get such a large variation in temperature. When we pair that with where there's trees, we can visually clearly see that our hotter areas here in the southern part of the county also have the least amount of tree cover, while our more forested and canopy cover rich parts of the county in the northeastern corner here is also our coolest area. At sort of that municipal level, we see about a 5.5 degree gradient in temperature on this particular day. For context, this region has experienced about a 1.5 degree increase in air temperature from climate change. And like I mentioned earlier, surface temperature is not the same as air temperature, but you can very clearly see this huge magnitude in temperature shift that is much larger than what we would see from climate change alone. And so this urbanization is really magnifying those warming conditions. What's kind of fun about this data is because that EcoStress sensor in particular can hit the same point many times over the course of a day, we can see how important trees are, not just in altering temperature, but sort of altering kind of the diurnal cycle of temperature. Like, how does it change over the course of the day? And so here I'm showing you some measurements from the summer of 2020, going from 7:30 in the morning to about 5 o'clock in the afternoon. And here's temperature as a function of canopy cover. And you can see early in the morning, there's still that cooling effect of trees, but as we go later and later in the day, as air temperatures get hotter and hotter and the angle of the sun gets higher and higher, you can see the importance of trees becomes more and more important. Right? And so this is really pointing out that it's not just that they cool things off, it's that they cool things off during the hottest times of the day when our people might be most vulnerable to those hot conditions. We look at this another way. If we look at this as a function of sort of how developed an area is or how much canopy cover an area has, what we find is that as you go from morning to afternoon to early evening, that range in temperature is highest where we have the highest intensity of development, and it's lowest where we have forest. So we can sort of think of trees and forests as kind of creating more even-keeled communities. There's just less variation in temperature during the day when we have forest than when we don't. And again, this has important implications for public health and energy demand, because it's really during these hot times of the day that we have the most issues. When we look at this across the 40 some odd municipalities in Westchester, we find this really tight relationship between land surface temperature and canopy cover. These axes should really be flipped here, but the relationship is sort of stays the same. But basically, as canopy cover declines, surface temperature increases considerably. In fact, of all of the variables variability in temperature across Westchester County, we can attribute 70% of that just to how many trees are in a neighborhood. There's other important things like elevation, how far you are from the water, things like that, but 70% can be explained just by where there's trees. This is looking at sort of the relationship with total canopy cover, which really includes the forest. If we want to take a more specific look at our communities where, unfortunately, I don't live in a forest, but we do have trees around my house. We want to look at the role of trees in our communities. We can sort of mask out the forest area. That's sort of this darker color here. The lighter greens are the trees in our yards, in our residential areas. We see the same relationship. The more canopy cover we have in our communities, the cooler things are. Here we can explain more than half of the variability in temperature across our municipalities just by how much tree cover is there. As a little exercise for how this can influence land use decisions, here's an example from Pleasantville. So what I want to show you, this is the spatial variations in surface temperature and how surface temperature has changed between 2011 and 2019. Now we expect some changes because just climate varies from year to year and things like that. But there's certain areas that really pop. So we see these really bright red areas in these two locations here, which may suggest that something has really changed, right? So these areas are both 4 degrees Celsius warmer than they were in 2011. So that's about 7 degrees Fahrenheit warmer. Here's some Google Earth imagery of what those places looked like in 2011. Both of these arrows refer to these red spots here. Now, if we look at those areas in 2019, you can clearly see that we lost forest and there's some development and there's this new condominium development here. And this really highlights how even at these small spatial scales, removing vegetation cover and putting buildings in can really, really change local climate conditions. We can also think about use this information to highlight where planting trees might have the greatest impact. So this blue line here just sort of indicates what we would expect the role of forest cover to be in canopy cover, right? So what this is saying is that if all of your canopy cover is driven by forest, your municipality would fall right on this blue line somewhere. And that's largely true for the municipalities that have more than 60% or so canopy cover. These areas where the municipal points, each one of these points is the canopy covering municipality, where it sits above that blue line is indicating that canopy cover is enhanced by trees that are in our backyards and along our streets. And so what we find is that it's really these municipalities with less than 20% canopy cover that have the largest variation, with less than 20% forest cover that have the largest variations in canopy cover. And there's been some work that suggests that 40% canopy cover is a threshold we want to get to sort of maximize the benefit of trees. You can argue that, but I'm just throwing a red line here to just separate that out. When we do that, we find that, okay, even though all of these areas have very little forest cover, there's about 1.5 degrees difference in surface temperature just based on how many trees have been planted in that community. Again, this is comparable to the amount of warming that's occurred from climate change. There's also an important socioeconomic component to this, especially for these low forest cover municipalities. Those that are the wealthiest have the most trees and are the coolest. And unfortunately, those that are the poorest have the fewest trees and are the hottest. And so we can use this sort of information to think about where we might want to focus our resources to help to alleviate some of the public health issues that might exist for our most vulnerable communities and where we can get the biggest bang for our buck for planting trees. We can also use these data to look at changes over time. So across Westchester, here's the changes in surface temperature of different cover types over time. We see these increases. Part of this is, of course, just from the fact that our climate is warming. We also see these changes in land cover types over time. We can look at these patterns over time and we can really start to learn a lot. So first, we know forest is declining. That's not a surprise. But these patterns do follow economic activity and there's a little bit of a lag, right? So in in 2008, we had that economic downturn, and it really wasn't until 2010, 2011 that we really saw the rate of forest decline slow. And it's probably because a lot of these projects got initiated before the downturn happened. We can also drill down a little bit deeper and think about, okay, well, what are our communities doing to minimize canopy loss, and is it working? These data that I'm showing you are very, very preliminary. We still have a lot of work to do on this, but basically we've been going through and trying to figure out which municipalities in Westchester have some sort of tree planting program and which ones don't. Here's a map showing the declines in canopy cover over time and where there are the largest declines. That's sort of the northern part of the county. Across the whole county, everyone's losing canopy cover. In this graph, I'm showing you the changes in canopy cover, but I'm separating this out between the communities that don't have any sort of tree planting program and those that do. There's a lot of variability in the data, but it's suggesting that the communities that have some sort of tree planting ordinance are losing canopy cover at a slower rate than those that don't. So it suggests that these sorts of things can work. We're trying to drill in a little bit deeper and better understand the nuances of these different programs to figure out what works and what doesn't. But at sort of a high level, it seems that these programs can be effective. We can also sort of figure out where are the forests most vulnerable and where might we want to focus our conservation efforts. So here again, I'm showing you a map of forest cover in Westchester. And then what we did is we looked at where are there forests that are protected, where are there forests that are on steep slopes and can't get developed, and where are there forests on protected wetlands, so these would be swamps that also can't really get developed, and then where are there forests on land that can be subdivided. And so doing all that, it creates this mosaic of colors of forests in these different categories, and we can look at some of the statistics. So it seems that nearly half of the forest in Westchester is in some sort of protected state. There's another bit that's probably fairly safe from development because it's on steep slopes, but there's also about 45% or so of the forest that is vulnerable to development because it's currently on land that is not protected and theoretically could be subdivided if a landowner wanted to do so. We can also use these data to understand carbon sequestration dynamics across Westchester. This is using data from the Forest Inventory and Analysis Program. This is a program through the US Forest Service. It's the world's most amazing forest inventory program. There's hundreds of thousands of plots across the country. In Westchester, there's just 22, but across New York State, there's 3,000 of these. These are plots that the Forest Service goes out to every 4 or 5 years or so to remeasure the trees that are there. And from that, we can get great information about carbon sequestration at the county scale, at the state scale, at the country scale. These are Westchester numbers. I didn't have time to pull the Rockland County numbers before this, but you can easily do that. Statewide, our forests on average are taking up about 70 megagrams of carbon per hectare per year just in tree growth. In Westchester, that amounts to about 107 megagrams of carbon per hectare per year. Westchester winds up having, this isn't sequestration, this is storage. Westchester has the most carbon dense forests anywhere in the state. But we can also look at how carbon storage is changing over time. In the state, our forests continue to accumulate carbon, right? So they continue to help to mitigate climate change. But in Westchester, while our forests may have a ton of carbon being stored in them, likely because of land cover change dynamics, they're losing carbon over time. And the way these data are calculated is such that this is indicating that it's more than just land cover change driving this. There might be something else, maybe it's invasive species or deer that are thwarting regeneration in our forests. Regardless of the cause, our forests are actually losing carbon over time rather than sequestering it. This is the second largest decline of anywhere in New York State. Coming back to some of the work I initially told you, we can think about how forest fragmentation in Westchester or in Rockland County might be influencing our estimates of carbon sequestration. The forest inventory and analysis data that I just showed you doesn't take into account these enhancements of growth that our work shows exist near forest edges. In Westchester, a quarter of the forest is being influenced by edges. You can see that in this map here. The yellows are all of the areas of forest that are located near an edge. Of course, what this looks like varies spatially between different parts of the county. And our estimates suggest that the enhancements near the edge increase carbon sequestration by about 16,000 tons per year above what we might estimate just using the forest inventory data alone. For context, that's the emissions of about 9,000 vehicles each year. I need to end this point just by throwing out this disclaimer that this does not at all mean that we should fragment our forests as a climate mitigation strategy. There's a couple of reasons for that. First, we know from decades of research that fragmentation has huge adverse impacts on biodiversity. But even just from a carbon sequestration perspective, to get a forest edge necessarily means that you have to lose forest area. And while the forests that remain on the landscape might be more productive, they're not productive enough to fully offset the carbon sink that existed before the forests were lost from the landscape. So don't go out and cut up your forest as a climate mitigation tool. This is really just to say that while fragmentation is a bad thing, from a carbon perspective, it's not as bad as we may have initially thought. So I'm just going to finish up with 2 slides showing some examples of how this can be used for Rockland County that we just put together kind of quickly. So here's a map of Rockland County. You can see the huge areas of forests in Harriman State Park and Kakiat Park, and then that sort of string of forest that follows the Palisades, and then the rest of the county is largely pretty heavily developed. So currently nearly half of the county is forested, but there's been a decline of nearly 16 square kilometers of forest since 2001. Also, about half of the county is developed. There's been an increase of nearly 17 square kilometers of developed area since 2001. So again, you can clearly see that we're sort of trading forest for development. And we also find that there's 53% canopy cover in Rockland County, but this has declined by about 5.5 square kilometers since 2011. I just underline this here because these land cover products go back to 2001, but the canopy cover currently only go back to 2011. But again, here you can see that there's a substantial proportion of total canopy cover in Rockland County that's from the trees in our communities, in addition to what's in our forests. Then we can look at how this might influence spatial patterns in temperature. So here's one of those land surface temperature maps. Of course, the Hudson River itself is cool. Harriman State Park is cool. And then you can see large variations in surface temperature based on how developed an area is, but also how much canopy cover there is, right? So I grew up in Spring Valley over here. That's one of the hotter areas. You can see Route 59, and here's Nanuet, and the heavily paved over areas there are quite hot. Here's New City over here. Here's Nyack. You can see the towns that are more highly developed areas really pop. And you can also see that it's those areas that have very little tree cover. So we can look at this and say, okay, if there's a way to increase canopy cover in these areas, we can go a long way to helping to cool things off. So with that, I'll end, give some time for questions. I often like to end with sort of a deviation from what JFK said. I think maybe this is what he meant. And I need to thank a lot of the people. This is certainly not everyone who's helped out with this work over the years and all of our funding sources. And then I'm happy to take any questions. Thank you.
Andy, I want to thank you so much for that presentation. That was really amazing. And I so appreciate you taking your results and making them relevant to Rockland. And I also found the fact that every time you came or discussed a really technical term, you were able to put it into lay people's terms. So thank you for that.
Oh, good. I hope I didn't lose anybody in the process.
So we do have some questions, actually. So one question is, ideally, how many trees would we have to plant? What is ideal? There's a concern because trees near houses, some people consider them a hazard. They can be dangerous. So how many trees do we need?
An endless number of trees. So yeah, so this is the trickiest thing about tree planting. I think oftentimes we're quite familiar with trees in our yards or on our along our streets when they fall down and like damage property or knock out power, right? Every time that happens where I live, within a couple of days, Con Edison is driving up and down the streets, cutting off branches and cutting down as many trees as they can. And so I would argue, like, I think we need to change our thinking about trees a little bit and not necessarily view it as tree, no tree, but where do you want to put a tree, and then thinking about what the best tree is to put there, right? So any tree is better than no tree. And if you're near a house or you're near a power line, maybe planting something like a dogwood or a redbud that will only get to be 30 feet or so tall and never jeopardize property in any meaningful way and never jeopardize power lines is a good way to go. You'll still get a transpiration benefit. You'll still get some shading benefit, not as much as if it were a huge oak or maple, but you also won't have to worry about the potential consequences of a tree coming down. And then maybe in a backyard a little bit further from a house, those are the great places to plant the trees that will live a long time and sequester a lot of carbon and do a lot of transpiration. So oaks are really good for that. I think that's also a good species to plant in the face of climate change. Kind of a fun fact about oaks is that we can sort of put trees into two different categories based on how they behaved when they're stressed for water. Some trees will sort of close up their stomata, which are these little pores on the leaves that control kind of gas exchange. And it's when those pores are open that water leaves and things can get cooled off. Maples close down under water stress. The oaks will keep transpiring away. And so if we're thinking about maximizing cooling benefits during hot days, the oaks might be a little bit better for that. Also, given that where we are, we're sort of like in the heart of an oak tree's range, we can probably expect them to do well under warming climate conditions. So I think it's not just the number of trees, it's the type of tree that we're planting, and maybe what we want to think about is getting towards certain thresholds of canopy cover and not just the individual trees, right? You can plant 30 trees that are each 8 feet tall, or have one tree that's 60 feet tall that is doing more work than all those little trees that you just planted, right? So, I think we want to take kind of a long-term view, know it takes trees a while to build out their canopies, and also think about the fact, well, when a large tree comes down, we typically just replace it with one little tree. And so we want to try and stay ahead of that and increase sort of the diversity of tree species that we plant, and also increase the diversity of tree ages that we have, so we don't have our entire canopy of trees turning over at the same time.
Thank you. Please comment on research about the benefits of trees along highway and road corridors for removing air pollutants, buffering noise, reducing heat island impacts, as well as carbon sequestration. In Rockland and other areas in the region, do you think there's much potential for achieving more benefits by planting and managing trees along these corridors in different ways?
So, I'm thinking about our highway corridors, and like a lot of our parkways, sort of by design, they are lined with trees, right? And so I don't know how much opportunity there is to increase that. I know in Westchester, maybe in sort of like southern parts of the county where a lot of that surrounding tree cover may have been lost, there's opportunities, but certainly that trees sort of form this physical barrier, and as emissions, like an important one is particulate matter that's 2.5 microns or smaller. These are the size of particulates that can really get lodged deep in our lungs and induce a suite of public health problems. This is the one that we think about most in terms of air quality. Trees are really good at intercepting those particles and sort of taking them out of the atmosphere. And so presumably having a bunch of trees along roadways, diesel exhaust is a huge source of this, that would help maybe to confine a higher proportion of those air pollutants to that corridor rather than spreading more widely, maybe to where people live. Trees also, when they're photosynthesizing and they have their stomata open, they're taking air pollutants in, and they can, in many cases, metabolize those air pollutants into things that are not toxic or just sort of incorporated into their biomass. In some cases, it may hurt the trees. In some cases, the trees may be sort of unaffected by it. But in doing that, they remove certain pollutants from the atmosphere, like things like ozone. The cooling benefits would be the sort of the same along road corridors that they would be in and around our community. So I think, really any of these places where we can plant trees and we can do it safely, we should be targeting those areas.
Speaking of trees, the emerald ash borer are killing a lot of trees in our area. I just noticed them in Harriman, huge numbers. Obviously, we're losing the benefit of the trees themselves, but is the subsequent decay and decomposition of these trees further exacerbating the impact in terms of CO2 levels?
Yeah, that's a good question. So yeah, the emerald ash borer has really decimated the ash resource. I do a lot of research at Black Rock Forest, and just in the past couple of years, I've seen large numbers of ash trees die. I think the thing with ash is it winds up being more of a biodiversity problem than a carbon problem. The reason that I say that is that they comprise a very small proportion of the total number of trees and the total amount of biomass in our forest. It's usually a couple of trees here and there. It's not like losing an oak or a maple tree that can make up 30 to 60% of all of the forest biomass. And these trees dying will get quickly replaced by other deciduous trees in the forest. Certainly when those trees come down, they'll decompose over the course of 20 years or so, and that will slowly release carbon back to the atmosphere. But in that context, a tree will replace it and essentially offset that increase in CO2. Trees dying and falling over and decomposing is sort of like a natural part of what happens in a forest. And generally speaking, new growth of trees are taking up more carbon than what's being released by the decomposition of those trees that fall. So as long as you're not having huge areas of forest die at once, like we do out west in response to the pine beetles, then losing a tree here or there, I don't think is really going to change the math on carbon sequestration in our forests a lot. The bigger impacts are going to be related to biodiversity.
One thing you didn't mention was conifers versus deciduous. So the question is, are deciduous better? And in terms of conifers, are pine trees, or particularly white pine, as effective as deciduous?
So generally speaking, our deciduous trees are probably more effective at cooling and mostly sequestering carbon than the conifers are. Pine trees can grow real fast, and so they can sequester a fair bit of carbon, but the carbon density or the wood density in our deciduous trees is considerably higher than in our conifers. So if we're thinking about any unit of volume growth, our deciduous trees like an oak or a maple is going to sequester far more carbon than that same volume of wood in a pine tree. Also, pine trees tend to do fairly well in dry areas, and their reason for that is that they can get by with very little water and they don't necessarily transpire a ton. And because they're not transpiring a ton, they're not going to be cooling off the area around them as efficiently as things like oaks and maple. So they can play an important role for aesthetics. They can be important for carbon sequestration. They do cool things off, just maybe not as effectively as some of the deciduous trees.
Okay. So here's a question about the town of Ramapo, which is in the western part of the county.
Yep.
They're going through a comprehensive planning process right now, and are developing a low density area in the northeast part of the town. So the question is, what would it take to develop an analysis like you talked about for Ramapo? So maybe using the Forest Service data or Landsat or other data sets?
Specifically, what things would you want to get at? Like what the current canopy cover is, what carbon sequestration currently is, or what are the variables that you think would be important to measure?
Well, I guess what existing conditions to begin with. And then if you could project, if it was possible to do that, to estimate future conditions.
Yeah, so the existing conditions, that's easy. That takes like 10 minutes of work, right? You just take these data layers like I showed you, and you just crunch the numbers within the municipal boundaries of Ramapo. You can get canopy cover, you can get different land cover types. Projecting what will happen in the future, it depends on which component you're thinking about. If you're thinking about the carbon piece, we've done a little bit of modeling work in Massachusetts that I suppose could be easily just exported to a town like Ramapo. Things are pretty similar, but it all requires like assumptions and different scenarios. So is this new development? Is the plan to just sort of cut down all the trees that are there and put a bunch of houses? Is it to carve lots out of existing forest? If it's the former, are there plans to plant trees? If there, you could potentially run scenarios with planting trees versus not planting trees and getting an idea of what that means for carbon sequestration over time. And you can also do some work to estimate what it might mean for local climate, at least from like a land surface temperature perspective. So those sorts of things can be done. It just all it depends on what exactly you're looking for.
So if residents were interested in doing that, can you give us some kind of ballpark estimate as to what it might cost if they hired a consultant? Off the top of your head.
Gosh. I mean, the land cover piece, like we could do that like for free in like 15 minutes. The projections moving forward, I need to think about a consultant that would have the expertise to do that. I'm not sure. I'd have to get back to you on.
Okay. All right.
Sorry.
Okay. No problem.
I'm much more steeped in the research side than like that sort of practitioner side. So it's been a while since I've been in that nonprofit world doing those sorts of things. But I can look into that and try and find some answer.
Well, I appreciate it though, Andy. Actually, you were very practical. I think we may have some land use board members watching today. And so I thought you really did give a lot of great ideas for them because they really are the stewards of our open spaces, of our forest in the county. So thank you for that.
Sure.
So I think that's it for questions. I want to thank you so much for spending the afternoon with us and giving us such a great presentation.
Sure.
You gave us a lot to think about. So thank you very much.
I noticed there was a question about solar panels and myelominivine. Do you want me to address those real quick?
I didn't. Please do. Yeah.
Okay. So I noticed the solar panel one because this is a question that comes up all the time. Do you remove forests and put solar panels, or what do you do? I don't know if that's exactly the essence of Marianne's question. So like in my house, I wanted to put solar panels on, but it was problematic because there were trees nearby that were creating too much shade. And so what do? Do you cut your trees down or do you put solar panels there? And it's a really difficult question to answer. And I think at that scale, it might be like a little bit of a personal preference. Like in my case, for example, the trees that are blocking it are not doing much from a carbon sequestration perspective. I live in a really dense area, and that was like the only buffer between me and my loud and sometimes annoying neighbors, right? So I wasn't too keen on getting rid of those trees. So if you just have a couple of small trees and that's the thing that's coming in the way of solar panels, you might think about pruning or maybe removing a tree and maybe in its place planting a tree in another part of your yard if you can. Generally, I hate saying this, and I don't have all of the numbers to back this up, but generally, a solar panel might make more efficient use of carbon than a tree does. There's lots of caveats there. I think there's still a lot of work to be done on the life cycle of making a solar panel and what the carbon emissions are, and also what the local climate impacts are of removing forests and replacing it with those dark surfaces of solar panels. But if you look at just the amount of energy a solar panel will offset from fossil fuel sources, it's probably going to be more than what a tree can sequester. I don't know what that math looks like when you start to factor in those sort of differences in local climate. But that question of tree versus solar panel is a tricky one. I would also argue that we should think about a variety of different aspects and services that we want from that tree, right? It's not just carbon, it's also aesthetics, it's also biodiversity. And so it's a little bit of a hand-waving question, and I apologize, I don't have a black and white answer, but there's just a lot of things to think about. So depending on the tree that is blocking the potential location of solar panels, you could think about getting rid of it and putting the tree in another part of your property, or maybe it's playing a critical role for other things and you don't want to get rid of it, and that makes sense too. The last piece is if it's a really large tree, it's not just the carbon that the tree is taking up, but the carbon that's going to be released back to the atmosphere once that tree gets cut down. So there's a lot of things to consider. And then the other question about mile and minute buying. So invasives are becoming a real problem, and a lot of this forest fragmentation edge work that we've been doing in Massachusetts, it's not as much of a problem yet. In much of upstate New York, it's not that much of a problem yet. Down here though, there's like porcelainberry and a whole suite of different invasive vines that really love forest edges and will just quickly crawl up the side of a forest. And I am certain those trees are far less productive than they would have been when they were in the forest. Most of those trees just wind up dying. And so that can really change the carbon math on what I showed you earlier. And I suspect that as the climate warms, and B, as these things get more of a hold around here, they're going to become more and more of a problem. So I think that the invasives do have an important role to play in carbon sequestration, and it's generally not a positive role.
So speaking of native versus invasives, we discussed losing a lot of ash trees to the emerald ash borer. So what would you suggest planting in their place? Someone commented that around Rockland Lake, they're planting tulip trees. And I'm just, what are your recommendations?
So, I mean, tulip tree, they grow fast, they get to be really large, they're going to do fine in a warming climate. We're sort of getting to the northern edge of their range, so I think that is fine. You know, like I said, oaks will do well. The unique thing about ash trees is that they leaf out a little bit later than our native trees, and from a biodiversity perspective, there's some data to suggest that this kind of creates these forest floor microenvironments that get more light, an extra couple of weeks of light in the early part of the spring that can be really favorable for different spring wildflowers. There's been some work in the White Mountains of New Hampshire that suggests that the density of things like trillium and stuff like that is higher around ash trees because they get like an extra week or so of light. So if you're thinking about it from a biodiversity perspective, maybe also thinking about a tree that has that later phenology. I'm not thinking of one off the top of my head, unfortunately. So if you're looking from a biodiversity perspective, that's something to consider. From just to replace trees, I think tulip trees are a fine option. They'll fit well with our changing climate. I think oaks will be a good option as well. Related to that, the other thing I will mention is at least in the community I live in, there's always these debates about, do you plant native trees or do you plant non-native trees? And I think we're always inclined to want to plant natives, and I would argue that where we could, we should. But I think a lot of the places where we're looking to plant trees are far from native conditions, right? Like these are things in tiny growing areas in sidewalks that are vastly different than what our trees have evolved for. And so I think there are cases when we could benefit from planting non-native trees that are also not invasive. So, you know, maybe things like London plane trees, right? Like they're not invasive. They will survive almost anything that you can throw at them in a city. And so in those places where it's not great growing conditions, I think it's okay to think about planting non-natives because there's still ecosystem services that they will provide.
All right, I think that's it, Andy.
Okay.
So thank you so very much. The comments are excellent, as I might expect. So thank you for joining us today. And we will have this, we will have a link for this recording, which I can send out. And with any luck at all, once I end this, we will have an evaluation link that pops up on your screen. So if everybody could take a moment and give us your thoughts, that would help us greatly. And also, if you will look in the future for emails from us on our Sustainable Landscape Program, which will be starting in March. All right, again, thank you, Andy.
Sure thing, and if anyone can feel free to email me if they have any questions they come up with later on.
Okay, excellent, thank you.
Have a good day, everybody.